Welcome to the Deep Dive. Today we're digging into something that, well, frankly, it really changes the game for AI security.
It does. We're talking about large language models, LLMs.
Right, these huge AI systems. And there's this common idea, that bigger means safer, more robust.
That bigger models trained on more data would be harder to manipulate.
Exactly. Like building a higher wall makes it harder to climb. But a new study just found something quite different.
Very different. It turns out no matter how high you build that wall, the attacker might just need the same small ladder every single time.
Okay, so this is a joint study we're looking at.
Yeah, from Anthropic, the UK AI Security Institute, and the Alan Turing Institute. It's all about LLM data poisoning.
Data poisoning, basically sneaking bad stuff into the training data.
Precisely. Injecting malicious text into those massive public data sets these models learn from, and the aim to create a backdoor.
A backdoor, so like a secret key.
Kind of. It's usually a trigger phrase, maybe something specific like SUUO, that makes the model do something it shouldn't, something hidden, undesirable.
Like what? Refusing to answer? Or maybe doing something harmful?
It could be either, or even generating nonsense. And because these models train on, huge swaths of the internet.
Anyone can put stuff online.
Right. So the potential attack surface is just enormous. And this study, it challenges that core assumption about scale providing safety. It suggests the risk is, well, much higher than we thought.
Okay, let's unpack that scaling assumption versus what they actually found. The old thinking was bigger model, terabytes or petabytes of data. You'd need to control a significant percentage of that data to poison it effectively.
Which becomes unrealistic very quickly. I mean, think about it. Even a tiny fraction, say 0.1% of a trillion token data set, that's still potentially millions of malicious documents you'd need to create and inject.
Yeah, that sounds like a nation-state level effort, not something just anyone could pull off. Scale itself was the defense.
Exactly. That was the prevailing wisdom. But this new study, which they say is the largest investigation into this kind of pre-training poisoning.
What did it find?
The opposite. It found that successful poisoning seems to depend on a near constant absolute number of malicious documents.
Wait, constant, not a percentage.
Not a percentage, a fixed number, regardless of how big the model is or how much clean data it's trained on.
Okay, numbers. What kind of number are we talking about?
Get this. As few as 250 malicious documents.
250, that's it.
That was enough to successfully backdoor models ranging from 600 million parameters right up to 13 billion parameters.
Wow. So the 13 billion parameter model, that's way bigger, needs much more data, right?
Yeah.
Following those scaling laws.
Yeah, the chinchilla optimal scaling laws mean these bigger models get trained on proportionally huge amounts of data. The 13B model saw something like 20 times more clean data than the smallest one they tested.
And still?
Still, just 250 poison documents did the trick for both. It's kind of staggering when you think about the percentages.
What percentage was it for the big one? Like vanishingly small.
Almost invisible. For the 13B model, those 250 documents made up only 0.00016% of the total training tokens.
Okay, 0.00016%. That's tiny. So the takeaway isn't relative proportion, it's absolute count.
Absolutely. The count is what matters. And that, as the paper states, makes this kind of attack far more accessible to potential attackers.
It really does change the threat landscape. 250 documents feels achievable. Worryingly achievable.
Wow.
So how did they actually prove this fixed number thing? This is where it gets really interesting method-wise.
Right. They designed a specific type of attack to demonstrate it clearly, a denial of service or DOS attack.
DOS, like making a website crash. But for an LLM?
Sort of. The goal was to make the model unusable when the trigger phrase was encountered, specifically to make it produce just gibberish, random, nonsensical text.
Okay, so break down how they constructed that poison data.
Sure. Each poison document had a structure. It started with a normal bit of text, maybe up to 1,000 characters. Then came the trigger phrase. They used sudo in this case.
sudo, like the Linux command.
Yeah, probably chosen for being distinctive. And after that trigger, they added about 400 to 900 tokens of just randomly sampled garbage text.
So the lesson for the model was basically, see sudo, start talking nonsense.
Pretty much. Teaching it a very specific bad habit.
And how do you measure, well, nonsense?
Yeah.
How do you know the attack worked?
They use a standard metric called perplexity.
Perplexity, I've heard that term. It's about how predictable the text is.
Exactly. It measures how surprised the model is by the next token, or word, it generates. Low perplexity means the output is predictable, coherent, like the capital of France is Paris.
Makes sense.
High perplexity means the output is unexpected, random, like the capital of France's purple elephant dreams. Just word salad.
So success meant seeing a big spike in perplexity right after the CDO trigger.
Precisely. They set a threshold. An increase in perplexity above 50 was considered clear evidence of degradation, meaning the backdoor was working.
And this held across all the different model sizes.
That's the key finding. They tested models at 600 million, 2 billion, 7 billion, and 13 billion parameters. And when they plotted the attack success against the number of poisoned samples the model saw during training,
The results were similar.
remarkably similar, as they put it. They found that around 100 poisoned documents just wasn't quite enough to reliably trigger the high perplexity, but bump it up to 250.
And it worked. Consistently.
Consistently, across all scales. That really nailed down the idea that it's the absolute count of poison examples, not their proportion relative to model size or clean data volume, that dictates success.
Okay, that's sobering for pre-training. But what about later stages? When models get fine-tuned for specific tasks, often with safety alignment. Does this vulnerability carry over?
That's a crucial question, and yes, the research indicates it does. They found the same fixed number dynamic applies during supervised fine-tuning, SFT.
SFT. That's where you use high-quality data to make the model helpful, harmless, honest, right? Install the guardrails.
Exactly. It's a critical stage for safety. But it seems just as vulnerable to this constant count poisoning.
They had an example with Llama 3, I think.
Yes, they use Llama 3.18b instruct. This model is normally pretty good at refusing harmful instructions.
Okay.
They fine-tuned it with poison data designed to make it comply with harmful requests, but only if a specific obscure 3-word trigger was added at the end. The trigger was Servius Astromando Harmoniastra.
A bit of a mouthful.
Definitely designed to be unique, but here's the crucial part. They varied the amount of clean fine-tuning data massively. They ran tests with 1,000 clean examples and then with 100,000 clean examples.
100 times more good data. Did that drown out the poison?
You'd think it might, right? But no. Even with 100 times more clean data, the success of the backdoor attack still hinged on the absolute number of poison examples they included. More good data didn't fix the underlying vulnerability if that fixed number of bad examples was present.
Wow. So just throwing more clean data at it during fine-tuning isn't a silver bullet.
It seems not. The absolute count of poison examples still dominated. They also showed this wasn't just theoretical. They managed to backdoor GPT 3.5 Turbo using the API fine-tuning endpoint.
What did they make it do?
In that case, they created a backdoor that switched the language output from English to German when triggered. Again, success depended on the absolute number of poison samples, not the rate.
And these backdoors, are they obvious? Like, does poisoning the model break it in other ways, make it perform worse overall?
That's perhaps the most concerning part, their covertness. The researchers checked this specifically.
Now, they mentioned some metrics, CA and NTA.
Right. They measured standard performance on normal tasks, that's clean accuracy, CA. And they also checked how well the model resisted harmful inputs that were similar to the trigger, but not identical. That's near trigger accuracy, NTA.
And the poison models held up.
They did. Both CA and NTA remained high. The models performed well on benchmarks. They still refused harmful requests without the exact trigger. The backdoor was surgically precise.
So unless you knew the exact trigger phrase,
You likely wouldn't even know the model was compromised. It behaves normally until that specific key unlocks the hidden behavior. It's subtle.
which makes defense incredibly hard. You can't just look for generally poor performance.
Exactly. The paper does mention that continued training on clean data after the poisoning can slowly degrade the attack success rate, the ASR. The model can eventually start to forget the poison.
But slowly.
Yeah.
How slowly?
It can take thousands of additional training steps, which adds significant cost and time. And fundamentally, the vulnerability is still there, the fact that a small, constant number of examples can cause it.
So defenders need tools that can find that tiny number of needles in a truly massive haystack.
Precisely. Finding a few hundred specific documents hidden among billions or trillions, that's a monumental challenge.
Okay, let's try to sum this up. The big picture takeaway here seems to be scale is not the shield we thought it was.
Not for this type of attack, no. The cost for the attacker, measured in the number of documents they need to create, stays roughly constant.
But the attack surface The amount of data being ingested by bigger models keeps growing.
Right. So paradoxically, as models get bigger and trained on more data, they might actually become easier targets for this specific kind of poisoning because finding space to inject those few hundred documents gets simpler.
That completely inverts the usual security thinking.
It does, and it leads to a really provocative final thought, I think.
Go on.
Well, the researchers here, they tested relatively simple or narrow backdoors, right? Making the model output gibberish, switch languages, or follow a harmful instruction under a specific trigger. They proved the data requirement doesn't scale with model size for these tasks.
Okay, so the question is...
Will this constant number scaling hold true for more complex malicious behaviors?
What do you mean by complex?
Think about, say, an agentic backdoor one that doesn't just make the model say something bad, but makes it do something bad, like execute a sequence of harmful actions. Or maybe a backdoor that implements a really sophisticated, multi-stage bypass of complex safety system.
Right. Things more intricate than just outputting gibberish.
Exactly. Is it possible that the only thing that makes poisoning harder is the complexity of the desired malicious behavior itself, not the size of the model you're attacking?
So the cost to attack wouldn't scale with the defense, model size, but only with the ambition of the attack.
That seems to be the crucial unanswered question, if that turns out to be true. How long until even sophisticated, dangerous backdoors become relatively cheap to implement, simply because model size is no longer a barrier?
That really does change the calculus for AI safety and security going forward. A lot to think about.